All right, welcome everybody. So in this video, I want to continue working with our examples from machine learning, working with regression models. We've previously looked at a regression model where we had one single predictor. In our example, that predictor was the literacy rate for a country as a percentage. And then we were trying to see how we can use that information to make predictions about the wealth of a country that we measure in GDP per capita in thousands of dollars. And we used this model to make some predictions, and we saw that not all of the predictions were great. So we might want to consider, well, why did I pick a model that only had one predictor? Maybe there's a better model to choose. So in general, there are an infinite number of models that we could pick. It doesn't even need to be a linear model. We could choose a quadratic model, we can choose an exponential model, and so on. So there are two things that we need to consider is what type of model are we going to use and what predictors are we going to include in our model. And we don't want to include all of the predictors because that's going to mean a number of things. First of all, it's going to take a lot of computational time. Secondly, it's going to be really, really difficult to make any sense out of any of the coefficients that come out of our model. Another problem might be that if I want to make a prediction about some unknown value, if I have all of the predictors in my model, this means I'm going to have to take some country and then record tons and tons of values for that country in order to get a good prediction. So there's always going to be this balance between how simple or complex do we want our model to be versus how good is this model at predicting things. And so in machine learning, what's really nice is rather than use a human, which may have some bias to say, well, I think this variable is going to matter and I don't think that variable is going to matter, we use computers to run tons and tons of models, and the computer is going to tell us which variables are most significant to include in the model. And so maybe we run tons of models, and we see that not only should we include the literacy rate of countries, but if in addition, we also include information about how healthy the country is, namely the life expectancy of the population in that country, and we also consider how large that country is in terms of square kilometers, thousands of square kilometers, this is going to give us a better way of predicting GDP per capita. So I can see that country A, they have a literacy rate of 31%, a life expectancy of 65 years, and their country is 653,000 square kilometers. And we've observed that their GDP per capita is $2,000. And here we've observed values for three other countries. I'm just calling them country A, B, C, and D. And so now let's take this additional information and figure out how we can fit a model that's going to predict the GDP per capita given three different predictor variables. Okay, so now let's consider how we can find the best fitting model to this data. And again, solving that problem is exactly the same as setting up a least squares problem and figuring out how we can minimize the sum of the squares of the error terms. And so all of these calculations that I'm about to go through, these are all done in a Colab notebook, which is linked in the description of this video. So you can open that notebook and play around with these calculations. But we would like to now find a model of the form where we're going to try and predict the wealth, which is GDP per capita. And that's going to depend on the literacy rate, the life expectancy, and the area of the country. So now we've got beta 0. We still have an intercept term, but now we have three different slopes, beta 1, beta 2, and beta 3. And we would like to solve this system. So in order to solve this system, we have the same equations. We just have larger matrices that we're working with. But we're still going to go ahead and solve for beta using the normal equations, which says we're going to take our model matrix X, take X transpose times X inverse, multiply that by X transpose, and then multiply that by the vector Y of observed values. So in this case, we set up our model matrix. Again, since we have a first term this intercept, which has a coefficient of 1 for all of our observations, we have a first column of ones, then we have a column of our observed literacy rates, then we have a column of our observed life expectancies, and then we have a column of our observed areas. We have our observed vector of response values, and these are the only two things that I need to solve for beta. So now I would plug in x and y into this equation. It involves, calculating products of 4x4 matrices and taking inverses of them. So again, I would encourage you to use technology, use Python to do these calculations, and we get approximately the following values for beta 0, 1, 2, and 3. So beta 0 is approximately minus 30.458. Beta 1 is approximately 0.067. Beta 2 is approximately 0.467. And beta 3 is 0.00003. So that's a really small value. So this gives us our model down below, where I've just plugged in the values for beta 0, 1, 2, and 3 into their appropriate slots in the formula. And then we can interpret these values very similar to how we did the model where we just had literacy. So for example, this minus 30 is giving me a prediction for the GDP per capita of the country when all of these variables are equal to 0. So a country that has a literacy rate of 0%, life expectancy of 0, and has no area. And there's no such country that would have those observations. So this intercept is not really telling us much information, because the predictor, the value of the predictors, is far removed from our observed values. We don't have any zeros in our observed values. We can see that the coefficient for literacy is a little bit less than what it was when we only had literacy in our model. So we can see the effect of literacy is now a little bit less severe than it was in our previous model. So if a country's literacy rate goes up by 1%, then their GDP and we assume that the life expectancy and the area are not changing. So if we just change the literacy rate by 1%, then the GDP per capita of the country is predicted to increase by $67, since this is in thousands. And if we increase the life expectancy of the country by 1 year and hold literacy rate and areas constant, we don't change them. So if the country just increases their life expectancy by 1 year, then their GDP per capita is predicted to go up by $0.467 thousand. So in other words, that's a $467 increase in their GDP per capita. We can see that the area coefficient here is really small, but that's because we're measuring area in pretty large units. So here we can see that if we increase area by 1,000 square kilometers, that the GDP per capita is barely expected to change. So maybe area is not really the best predictor to include in our model, since it doesn't seem to have much value at predicting things. So these coefficients tell us how the response variable is predicted to change if we only change that one variable and keep the others the same. So if I'm a country and I want to increase my GDP per capita and I'm looking at this model, well, we probably can't increase the area of our country, but maybe I've got a budget. I want to think about, should we invest that into our education system or into our health system? And this model is telling me it's probably a better investment to invest that in our health system, and that's going to have a better predicted increase in the wealth of the country than if we invested in education and tried to improve the literacy rate. Of course, improving both of these things would be ideal, and that would have an even larger effect on increasing the wealth of the country.